Hello everyone, welcome to my channel. In this video I'm going to talk about hash indexes in In-Memory OLTP. Let's get started. Before moving forward, I highly recommend you watching my previous video on multi-version concurrency control in In-Memory OLTP to fully understand this video. When we create in-memory OLTP tables, we have to specify indexes, right? Without specifying indexes, we cannot create a table. We can create up to 8 indexes per table, as you might know, and you cannot alter indexes later after creating the table. If you alter index, the table is recreated. Therefore, while creating table, please be careful. There are two types of indexes you can create in In-Memory OLTP, hash index and range index. Here, I'm going to talk about hash index. Before moving forward, let's learn row structure in In-Memory OLTP tables. In In-Memory OLTP tables, row structure is different from the on-disk rows. All Hekaton rows are saved in this form, as you can see. There is a header and payload part. Header part starts with begin TS. This is the insert timestamp. This is the transaction commit time, which inserted this row. We call this time, but this is just actually a counter. Then comes NTS. This is a delete timestamp. This is a transaction commit time, or we can call it counter, which deleted this row. Then comes statement ID of the statement, which inserted this row. Then IDX link count, number of indexes that reference this row. In our case, we have one hash index, so this should be equal to 1. Then comes padding. Then after padding, there is a pointer. This is a pointer to the next row in each index. We can create up to 8 indexes per table in Hekaton, so we can have up to 8 pointers here. Now, since we have only one index, we have one pointer. Last one is data payload. This is where actual data and index is saved. This structure of the row helps to provide concurrency in Hekaton tables. So every time you insert a row to a Hekaton table, rows are saved in this form in memory. Let's get back to index. When you create a table with hash index, firstly, hash table is created with hash buckets in memory. The bucket count is specified by you. Here I specified bucket count as 26 on column called middle name. Each bucket stores a pointer to the first available row location in memory. Okay? So let's see how following select query works. If you run this query, SQL Server applies hash function on the given value in where clause. Here it is A, right? And finds respective bucket for this value. This bucket has a pointer to the first required row. Now you can ask, we found first row, what about next row, right? As I told you already, every row internally keeps the link to the next row per index. After finding first row, hash bucket is not used anymore. The search is automatically goes to the next row based on the next row pointer saved in the row. As a result, all available rows are returned to the user. Okay? We have seen a case for one index. What if we had 2 indexes? Let's see. Imagine we created a table with 2 indexes. In this case, we will have 2 hash tables. Let's see how select query works in this case. The same process also happens here, only here hash function is for 2 hash tables. Okay? 2 hash tables are scanned and the rows are found for each condition. To the client, only the common rows are returned, as shown here in black marked row. Okay? So, if more than 2 indexes are implemented, the same logic applies. Pretty straightforward, right? The number of hash buckets is an important factor for performance. If you choose hash bucket count lower than the expected cardinality of your target column, you will have many hash collisions. For example, if we choose bucket count equal to 5, in our case, instead of 26, we will have A, B, C, D, E, F values assigned to the first bucket, right? As a result, collision occurs, leading to slow performance in your queries. Furthermore, we should also be careful in setting too big bucket size. Firstly, SQL Server uses 8 bytes per bucket, which may lead to memory space waste. Secondly, SQL Server should search for many buckets to find target bucket. That makes index search time-consuming. Okay? We can tune the number of buckets by using following DMV. This DMV return hash chain length and number of buckets. If average hash chain length in your output is large, it means that many rows are chained to the same bucket. This may be due to low bucket count chosen or many duplicate values assigned to the same bucket. On the other hand, if average hash chain length is very small, you can expect that high empty bucket count. It means you chose very high bucket count while creating your table. Okay? So we learned about hash indexes today. In the next section, I'm going to talk about another type of index in In-Memory OLTP, which is range index. Please stay tuned and do not forget to subscribe. Thank you.